Hello everyone, my name is Cedrik Schüler and I'm from the Communication Networks Institute of the TU Dortmund University. In this talk I'm going to present our work towards machine learning enabled context adaptation for reliable aerial mesh routing. This presentation is structured as follows. After depicting the motivation, I will give a short overview of the PARRoT routing protocol. Afterwards, I will present our approach, discuss the results and give an outlook and future work. Aerial mesh networks realized by UAVs can fulfill different kinds of tasks, like network provisioning, video surveillance, and others. Besides the fact that they have to deal with high agent mobilities and therefore are dynamic network topologies, which already sets high requirements to the routing algorithm itself, operators want to deploy them fast and anywhere. If we look at the map of Dortmund on the right, we can classify the inner part here as an urban radio environmental prototype, because we have densely located buildings and can expect lots of multipath propagation here. As long as the UAV swarm stays within this area, we are talking about a single REP scenario where the task is to have a fast deployment of the UAV swarm. If we now consider this part of the map, we have sparely located buildings and therefore find a different radio environmental prototype where a different configuration may be needed. This holds as well for the outer part here, where we have no buildings and signal attenuation mainly occurs due to distance effects. If the UAV swarm now performs a transition across these REPs, we are talking about a multi-REP scenario where the challenge is to have a dynamic reconfiguration during runtime. To enable all this, our proposal in this work is the Context-Adaptive PARRoT routing protocol, which is featured by a machine learning based REP classification to have an autonomous parameter selection. Before going into the details of our new protocol, I will give a short overview about the PARRoT routing protocol. Predictive Ad-hoc Routing, fueled by reinforcement learning and trajectory knowledge, is our previous work and was presented at the 2021 VTC Spring Conference, where it was awarded as the best student paper. It consists of three core components, which are wings, a trajectory prediction, chirp, which describes the periodic dissemination scheme we use, which is necessary to maintain a decentralized network architecture, and brain, which is the reinforcement learning based routing decision making. Although PARRoT could outperform most reference protocols, it uses a static configuration, where we have seen potential for improvement for the deployment in different REPs. The wings module was extended with an additional parameter to be more variable to match different REPs. The chirp process was adapted to enhance the robustness against short-term effects, and the brain component was evolved to a hybrid machine learning approach by adding a machine learning-based REP classifier. Here we see the Q-learning formula which is used in PARRoT. We have a neighbor-specific discount factor which consists of three partial metrics. The first one is gamma 0, which is a constant parameter and guarantees the path degradation which is necessary to ensure a loop-free routing process. The second one is VLET, which is the value for the link expiry time between two agents. And the third one is V-cohesion, which describes the neighborship relations of agents. The following metric extension by the range budget focuses on the metric VLET, and this works as follows. The agents predict their trajectory towards a future position. We assume a communication range RTX, which is derived from a free space pathless model. The metric VLET now tries to assess this region of link availability here, and therefore it depends on the assumed communication range RTX. When we are talking about different radio environmental prototypes, the effective communication ranges may vary with different REPs. So what we did here is to add a parameter range budget RB to make this adjustable. The resulting calculation is shown here, where we have the previously assumed communication range RTX, which is then modified by the range budget and is compared with respect to the relative agent trajectories. Each agent periodically creates routing messages called chirps, which contain identification data, a time to live, metrics, and mobility information. These messages are broadcasted every 500 milliseconds and are then forwarded over multiple hops by other agents after updating the information with their own assessments. In this way, they collaboratively share the necessary information. These principles were not changed in CA-PARRoT, but the process was modified at the receiving agent and can be divided into 4 phases. First, the agent receives an incoming chirp and stores the information about the neighbor. If the information is more recent or of a higher value, this leads to phase 2, where a reinforcement learning update is triggered here. In phase 3, the temporary knowledge is used for the further dissemination of the chirp. This does not differ much from PARRoT, despite the fact that the knowledge here in phase 3 is only temporary and does not lead to an update of the local queue table, which made the queue table in PARRoT very unstable and thus caused performance drains. To overcome this issue, we use the metric buffer here, which is used to store the information from phase 1 and is then released by a timer here, which is synchronized to the chirp initialization timer. So every 500 milliseconds the metric buffer is released, and only the best candidate is to use to trigger another reinforcement learning update, which is then used to update the local queue table and also to refresh the routing table. So the best available route from this step is used for the routing process. At this point, we add weighting coefficients lambda and omega to have the option to give the partial metrics phi-LET and phi-cohesion more or less weighting depending on the classified REP. We also introduce our toolchain to classify the REP, which consists of the continuous monitoring of received signal strength and distance pairs for every incoming chirp, which are then used for a feature extraction, and the features are fed into a machine learning classifier to classify the REP. And knowing the REP, we can now select appropriate parameters from a database here. Having this instance, we want to reduce the amount of recalculations of the REP to add robustness to the whole process, but if we have a new REP, we want to validate it fast. We did this by implementing a backup counter mechanism. So we have a counter which is decreased on every timer-based update. If the counter is greater than 0, we do not re-evaluate the REP. But if it reaches 0, we trigger the machine learning based classifier and have our new REP result. If the REP is consistent, we exponentially grow the counter and reset it. But if the REP changed, we set the counter to 1. So this leads to an immediate re-evaluation in the next iteration step. Before presenting the results, I want to discuss the use methodology briefly. We evaluated for a 3-dimensional playground with 10 UAV agents. The agents have a speed of 50 km per hour and follow a controlled waypoint mobility, which is the well-known random waypoint mobility pattern shown on the right, with the extension that randomly sampled future waypoints can be queried by the Wings module to enable the cross-layer trajectory prediction. 2 of the agents establish a UDP video stream with a constant bitrate of 2 megabits per second, which we analyze for the packet delivery ratio and the end-to-end latency. Summarized, we aim to reproduce the simulation setup of our previous PARRoT paper to ensure a good comparability. As reference protocols, we compare CA-PARRoT with the well-known reactive AODV, the proactive OLSR, and the gear-based GPSR. In addition to those, Mobile and PARRoT as mobility predictive protocols were also considered. First, we evaluate the quality of our proposed REP classification. The training and testing was done with the limits framework, and here we considered 3 different machine learning models, which are artificial neural networks, random forest, and linear support vector machines. On the right, we see the 10-fold cross-validation accuracy. We see a high accuracy for all considered models above 95%. However, the random forest model here shows the best performance and is therefore exported as C++ code from limits and embedded into the CA-PARRoT simulation model. In order to choose parameters for any classified radio environmental prototype, we carried out parameter optimizations for each REP. For example, for the new introduced range budget, we observe a peak value for the PDR in a rural prototype. On the other hand, for the urban prototype, we observe an increasing PDR as well as an increasing latency. So here the selection is a trade-off between these 2 KPIs. We further analyze the different pairs of weighting coefficients lambda and omega, as seen in the heat map on the right. All in all, this has led to the shown table of parameters, which served as a database in CA-PARRoT to select parameters based on the classified REP. Here are the results of the routing performance evaluation in a rural radio environmental prototype. As seen here, CA-PARRoT significantly outperforms all considered established reference protocols. Also compared to PARRoT, we achieve a gain of 3%, which means that this is a further step towards the upper bound, which is a mobility constraint limitation, as routes are not always available. The two PARRoT protocols also have the lowest latency, whereas CA-PARRoT is even lower in means. The urban prototype is characterized by lots of multipath propagation and thus a lot of short-term effects. In our previous work, we found out that PARRoT shows a lower performance than BAT-mobile because every incoming chirp was used to perform a reinforcement learning iteration. This behavior made the Q table in PARRoT very unstable and harmed the reliability of routes. With the new timer-based update process and autonomously selected parameters, CA-PARRoT has significantly improved in this aspect. CA-PARRoT has now the best performance of all considered routing protocols and can outperform the established ones by up to 23%. Compared to PARRoT, we have a performance gain of 11%, which means that CA-PARRoT has now a 5% better PDR than BAT-mobile. Also, the latency as a second KPI shows improvements. CA-PARRoT is 9% lower than BAT-mobile here and 23% lower than PARRoT. Compared to the established routing protocols, this means an up to 50% lower latency for this urban prototype. In this work, we propose our novel routing protocol CA-PARRoT. It enhances the PARRoT protocol by new parameters and a timer-based update process to compensate the impact of short-term effects. We also analyze machine learning approaches to classify radio environmental prototypes from continuous signal monitoring data to enable the autonomous parameter selection. The presented changes made CA-PARRoT to achieve key performance indicators up to 23% better than PARRoT and an up to 50% higher performance than the considered well-known reference protocols. In future research, we aim to consider more radio environmental prototypes and include more features for the classification task. We also want to analyze multi-REP scenarios where the agents perform a transition across REPs. Also, the knowledge of the current radio environmental prototype enables prototype-dependent optimization techniques. The simulation model is available online under the shown link. Thank you for your attention. If you have any questions, feel free to ask them or to contact me via email.